Usually when we talk about a medical diagnosis, there's this expectation of precision.
Oh, absolutely.
It's like engineering or something. You break your arm, the X-ray shows that jagged white line, and the
Mhm.
doctor just points and says, there it is.
Right. It's binary, it's clean, and
Mhm.
fundamentally, I mean, it is comforting. We like things in life to be visible, to be categorized neatly into boxes, broken or not broken.
Yeah, exactly.
Yeah.
But then you step into the world of teaching a computer how to actually hold a conversation with a human being,
Yeah.
and suddenly that beautiful, precise X-ray machine is just completely
Nothing.
shattered.
Oh, completely.
We're looking at a diagnostic landscape that is, well, honestly, it's murky. Because human language is the furthest thing from binary. It is messy, it is completely full of unspoken assumptions, and it is, frankly, just incredibly chaotic.
It is the absolute definition of diagnostic muddy waters.
Ah.
Trying to get a machine to not just hear the literal words you are saying, but to actually understand your underlying intent and then, execute a real-world task based on that messy language.
Um,
It is one of the most complex challenges in all of AI right now.
And that is exactly what we are decoding for you today. If you are joining us, we are taking a massive stack of incredibly dense, expert-level research into task-oriented dialogue.
Specifically pulling from the foundational frameworks developed by Meta AI.
Right. And we are turning it into your personal roadmap.
Yeah.
If you have ever, yelled at an automated phone tree because it kept saying, I didn't quite get that.
Which we all have.
We all have. Or if you're just insanely curious about how the digital assistants in your living room actually figure out what you want, well, this deep dive is built for you. We are going to trace the entire life cycle of a request.
From the very moment you speak.
Exactly. Through the machine's ears, deep into its brain, and finally out through its mouth. Okay, let's unpack this, starting with what we even mean by task-oriented.
Right, because definitions matter here.
They really do.
Yeah.
Because there's a big difference between chatting with an AI about the meaning of life and asking a bot to actually do something for you in the real world, right?
Precisely. And that distinction is the foundational bedrock of this entire field of study. We really have to clearly separate open domain chatbots from task-oriented dialogue systems.
Okay, so an open domain system, that's like the massive language models you might interact with online.
Yes. They are essentially designed for idle chat. You can talk to it about 18th century philosophy or, I don't know, ask it to write a sonnet about your golden retriever.
Right, and success there is pretty subjective.
Exactly. Success is really just defined by whether the response sounds fluent, grammatically correct, and somewhat relevant to your prompt. The stakes are incredibly low.
But a task-oriented system is different.
Very different. It exists for a singular, highly specific purpose. To accomplish a measurable goal that you, the user, have described using natural, unstructured language.
So we're talking about tangible actions, like navigating a house robot to the kitchen to grab a beer,
Or booking a flight from Chicago to Tokyo.
or securely transferring $500 from checking to savings. There is a definitive, undeniable finish line to the conversation. Either the money moved or it didn't.
Exactly. And to reach that finish line, the dialogue has to exhibit three major characteristics that humans do completely subconsciously. But machines find them incredibly difficult.
Okay, I'm taking notes. What's the first characteristic?
The first characteristic is turn-taking. Human dialogue is interleaved. I speak, I hold the floor, and then I signal, maybe through a pause or my intonation, that it is your turn to speak.
Right, or I ask a direct question.
Right. The system has to inherently understand this rhythm. It has to know when you are actually done speaking so it can take its turn to process the information and respond.
Which sounds completely trivial until you actually listen to how humans talk. We pause to think all the time. We say, ah. Like, if I say to a digital assistant, I want a flight to, Boston, I absolutely do not want the bot cutting me off at, and booking a one-way ticket to nowhere.
And that happens constantly with poorly designed systems. Turn-taking is mathematically and acoustically complex because silence does not always equal the end of a thought.
Yeah, that makes sense. So what's the second characteristic?
The second major characteristic we need to look at is what linguists refer to as speech acts.
Speech acts, okay.
This is the core concept, that when we speak, we aren't just exchanging dictionary definitions. We are actively performing functions. The research breaks these down into four specific categories.
Lay them on me.
The first is assertives, where the speaker is putting forward information, stating a fact, or suggesting a time. The second is directives, where you are actively requesting information or commanding the system to perform an action.
Give me an example of a directive, like, find me a Thai restaurant that's open late. That's a directive.
Yes, that is a classic directive. You are directing the flow of action. The third category is commissives.
Commissives.
Right. This is where the speaker is committing to a future action, agreeing or opposing, saying yes, saying no, or finalizing a choice.
Got it. And the fourth?
And finally, the fourth category is expressives, which are basically the social lubricants of conversation. Saying hello, apologizing, saying goodbye, or saying thank you.
Hold on. I want to make sure I'm visualizing this correctly. This seems like a lot of categorization for a machine to handle. So if I walk up to my phone and say, I want a pepperoni pizza, that is a directive. I am telling it to do something.
Correct.
But if the system comes back and asks, do you want extra cheese on that? And I reply, yeah, definitely. Definitely is a commissive.
If we connect this to the bigger picture, that categorization is exactly what separates a frustrating, archaic, automated phone menu from a genuinely helpful AI assistant.
How so?
Well, an old-school phone menu doesn't understand the nuance of speech acts. It only understands a binary input, like press 1. A sophisticated, modern, task-oriented system maps your messy, conversational speech acts into logical database operations it can execute.
Oh, wow.
Yeah, it knows that your commissive, yeah, definitely, is actually authorizing a specific variable in its code to be changed to true.
Okay, I see. It's secretly translating our casual banter into rigid code. That is wild. So that's turn-taking and speech acts. What is the third characteristic?
Grounding. And this might be the most crucial one for user experience.
Grounding, what does that mean?
Grounding is the process where the agent and the user mutually agree on and acknowledge the information that was just exchanged. It's about establishing a shared reality.
Okay, I think I need an example for that one.
Imagine you ask a human travel agent to book a flight to Miami. If they just stare at you blankly in total silence and start typing furiously on their keyboard, you have no idea if they heard Miami or Milwaukee or Mali.
Right, you'd be sitting there panicking.
Exactly. Grounding is the agent saying, okay, looking for flights to Miami before moving to the next step.
I get it. It's the confirmation ping. It's the psychological reassurance that we are on the same page.
Precisely. And achieving all three of these things, seamless turn-taking, accurately classifying speech acts, and natural grounding, is phenomenally difficult because the history of any given dialogue is just incredibly noisy.
You see how?
Well, humans use pronouns constantly, what linguists call anaphora. We'll say something like, book the flight for tomorrow, and then 2 minutes later in the conversation say, actually cancel it.
Oh, right.
The machine has to instantly trace back through the dialogue history to figure out what it refers to.
Right, because it could be the flight, the rental car, or the hotel reservation we talk about in between.
Exactly. And beyond the linguistic noise, you have massive engineering hurdles. These systems have to interact with external APIs, the actual web services of airlines, banks, and restaurants to actually do the task.
And those update constantly.
Constantly. Plus, the vocabulary is hyper-specific.
Mm.
The way you talk about a checking account is entirely different from the way you talk about ordering a pizza.
So, to stop the machine from just drowning in all this unstructured, chaotic human language, the engineers have to give it a structural vocabulary, a way to logically organize the entire world. And looking at the architecture, this structural vocabulary is built on three main pillars: domains, intents, and slots.
Yes. This is the ultimate filtering mechanism. Without these three pillars, the system is just staring at a wall of random text, completely paralyzed.
Let's break them down.
Oh, let's start at the top. The domain is the broadest possible category of the conversation. Are we talking about the weather? Are we talking about commercial flights? Are we browsing a restaurant database? The system has to establish the domain immediately because that tells it which knowledge base to activate.
You know, I always think of it like walking into a massive multi-level department store.
Yeah.
The domain is the system figuring out if you need the shoe department, the home goods department, or the electronics department.
That's a great way to picture it.
Right, because if you start talking about size 10, the system desperately needs to know if it's looking at sneakers or televisions.
That is a perfect analogy. You have to be in the right department first. Once the system knows your domain, it needs to lock onto your intent.
The intent. Okay.
Intents are the specific classes of action that the user wants to initiate within that particular domain. So if we are in the flights domain, the intents might be book a flight, cancel an existing reservation, or check the arrival time of a specific flight.
Okay, so I am in the shoe department. That's the domain. My intent is either buy running shoes or return these boots I bought last week. It's the core action.
Yes.
And then we hit the third pillar, which is slots. This is a term that gets thrown around a lot in AI architecture. What exactly is a slot in this context?
Slots are the highly specific entities, the exact spans of text, that are absolutely mathematically required to fulfill the intent. They are the essential variables in the equation.
Okay, let's look at an incredibly detailed example then.
Sure, imagine the system has identified that your intent is to book a flight. To actually execute that command in the airline's database, the system cannot leave certain variables blank. It has a rigid checklist of slots it must fill.
Like what?
Arrival location,
Yeah.
departure location, arrival time, departure time, date, passenger count.
So if I walk up to the digital assistant and say, I need to fly out of Atlanta next Tuesday in the morning, the system immediately fires up its filters.
Right.
Domain, flights, intent, book a flight. And then it starts filling in its slots based on my sentence. Departure location slot is Atlanta. Departure time slot is Tuesday morning.
Exactly.
But the arrival location slot is completely empty. I never said where I was going. So because of its grounding and turn-taking programming, it knows it cannot proceed. It has to ask me a directive question like, where are you flying to?
Exactly. The system uses those empty slots as a conversational checklist to aggressively drive the dialogue forward. It takes your unstructured human desire, I want to go somewhere, and forces it into a highly structured, executable template. It won't let you leave the conversation until the mandatory slots are filled.
But this is where we hit a massive physical bottleneck. Because before the system can categorize any of these intents or pull any of these slot values out of a sentence, it actually has to hear you.
It does.
It has to take the raw sound waves traveling through the air in your living room and turn them into digital text.
Right. It's the front door to the entire house. We call it automatic speech recognition, or ASR. And if the front door is jammed, the rest of the beautifully designed house doesn't matter.
So how does ASR actually work? Because it feels like magic when it works, and it feels incredibly stupid when it doesn't.
It is a fascinating multi-stage translation process of physics into mathematics. First, the system has to perform what is called endpointing.
Endpointing.
Yes. It is constantly receiving a continuous stream of audio from its microphone. It has to intelligently slice that audio pie, separating the actual human speech segments from the dog barking in the background, your breathing, and the silences between your words.
That alone sounds incredibly difficult. Distinguishing a sigh from a softly spoken word.
It is very difficult. But once it isolates a speech segment, it extracts the acoustic features. It analyzes the frequencies and amplitudes of your sound waves and translates them into a phonemic sequence.
Okay, phonemes, those are the distinct units of sound in a language, right?
Yes, think of them as the mathematical approximations of syllables. Then it takes those phonemes and tries to translate them into subwords or full text words.
And it does that blindly, just matching sounds to a dictionary.
Not blindly. It is heavily conditioned by a language model. The language model acts as a probabilistic referee.
A referee.
Yes. It looks at the sequence of sounds and predicts what words are most statistically likely to appear next to each other in English. If it hears a sound like to, the language model decides if it should be spelled T-O, T-O-O, or T-W-O based on the surrounding context.
But this translation from airwaves to text is incredibly fragile. I really want to highlight a massive issue that comes up in the research called the OOV problem, out of vocabulary, because this seems to be where task-oriented systems crash the hardest.
Yes, the OOV problem is a critical, persistent point of failure. As we just established, to successfully complete a task, the system desperately needs to fill its slots.
Right.
And slot values are very often named entities. They are the names of specific, trendy new restaurants, obscure foreign cities, or highly unique human names. These highly specific nouns are frequently completely out of vocabulary for the speech recognizer's general training data.
Right. I think about this all the time with music. If I ask my smart speaker to play the band Krong Bin, the acoustic model is going to hear that completely bizarre sequence of phones and absolutely panic because it's not a standard English word. And conversational speech makes this 10 times worse. We mumble, we speak quickly, we slur our words together, we have regional accents. It is not like someone sitting in a quiet room carefully dictating a formal business letter.
Which brings up a massive debate in the AI community. How do we actually measure if the ASR module is doing a good job?
How do they measure it now?
Historically, the industry has relied on metrics like word error rate, or U, and character error rate, CER. These metrics simply take the machine's transcript and compare it to a perfect human transcript. They measure what percentage of the total words the machine got wrong.
Okay, but I have to push back on this because using word error rate for a task-oriented system seems profoundly stupid.
Okay, let's hear it.
Hear me out. If I say to my phone, book a flight to Miami, and the ASR system hears, book the flight to Miami,
Okay.
the word error rate flags that as an error. It penalizes the system because A became the.
Right.
But honestly, who cares? It captured the intent, booking a flight, and it captured the crucial slot, Miami. The task can be completed flawlessly. Penalizing the system for mixing up an article in the middle of the sentence seems entirely beside the point of why the system exists.
You are touching on a vital paradigm-shifting realization in how we evaluate these architectures. Your frustration is entirely validated by the data.
Oh, really? Good.
For open domain dictation, say, automatically generating closed captions for a YouTube video, word error rate absolutely matters. You want every word perfect. But for task-oriented dialogue, the superior, far more relevant metric is slot error rate.
Slot error rate. I love that. It essentially ignores the fluff and asks one critical question. Did you capture the actionable data?
Exactly. Slot error rate doesn't care if the ASR hallucinates a few grammatical filler words or stumbles over an article, as long as the crucial, actionable information, the actual slot values, are extracted accurately.
That makes so much more sense.
It forces the evaluation to focus strictly on task success rather than pedantic transcription perfection. It aligns the metric with the user's actual goal.
Right, so let's assume the front door does its job. The ASR captures the audio. Maybe it scrambles a few filler words, but it gets the core text, and the slot error rate is low. Now that raw text moves deeper into the machine. We enter the actual brain of the operation. This is natural language understanding, or NLU. The system has the words, but now it must decode the meaning behind them.
The NLU module is where the really heavy cognitive lifting happens. The architecture breaks this down into 3 distinct sequential phases. Phase 1 is intent prediction, which we've already covered, determining the overarching goal of the user's utterance.
Right.
Phase 2 is slot filling, actively extracting the relevant entities from the text sequence. But Phase 3 is where it gets incredibly complex. State tracking.
State tracking. Just the phrase sounds intent. It sounds like the system is constantly keeping a running mathematical tally of the entire conversation.
That is a highly accurate way to conceptualize it. Dialogue state tracking is the system's short-term memory, but it's not just a static list. It is maintaining a probabilistic distribution of slot values as the conversation progresses over multiple turns.
Wait, probabilistic, so it's guessing.
It is constantly updating its beliefs about what you want turn by turn. And these 3 phases, intent, slots, and state tracking, face immense real-world challenges. ASR errors can mangle the exact positions of slots within a sentence, throwing off the extraction algorithms. Human language is inherently ambiguous, and users constantly use synonyms that the system has to instantly map back to a core concept.
To really illustrate how wild state tracking can get, I want to walk through an example from the research involving a music recommendation system. Let's say a user walks in and says, I'm interested in Wolfgang Mozart.
Okay.
The NLU kicks into gear, intent prediction fires, the user wants to listen to music. Slot filling scans the text and successfully extracts Wolfgang for the artist's first name slot and Mozart for the artist's last name slot.
But the state tracker simultaneously realizes that the album slot and the track slot are completely empty. The user did not specify a song. So the system has to make a calculated decision based on that current state.
What are its options?
Well, it can annoy the user by asking, which specific track do you want? Or it can simply acknowledge the request, use the slot data it has, and queue up a popular Mozart playlist, determining that it has enough state data to perform a generally acceptable action.
That's a relatively simple, linear interaction. But the research details an interaction from something called the Cambridge Restaurant System, which perfectly highlights just how insanely complex human conversations get and why state tracking is so vital. Let's play this out.
Go for it.
The user initiates the dialogue. I'm looking for an expensive restaurant in the center of town.
Okay, the NLU instantly fires. It identifies the domain, restaurants, intent, find a restaurant, it fills 2 slots. The price range slot is tagged as expensive, and the location slot is tagged as center of town.
The system checks its back-end database and replies, there are 33 restaurants that match. It's trying to narrow the field, so it asks a directive question about cuisine. What kind of food would you like?
Okay.
The user replies, I don't care about specific cuisine.
Notice the sophisticated state tracking happening right there. The system doesn't just leave the cuisine slot empty. It has to actively update the cuisine slot to a wildcard or any value, while mathematically maintaining the expensive and center-of-town constraints from the previous turn. It's holding all those variables in its active memory.
Right. So the system randomly selects one and offers a choice. How about the Varsity restaurant? The user says, great, reserve a table there. The system asks for the time and a party size. The user provides them. 8 p.m. for 2 people. Slots filled. The reservation is booked via the API.
The core task is complete.
The core task is complete.
Right.
But then the user throws a massive curveball. They say, okay, now I need a place to stay.
What's fascinating here is the immediate, complex, core-fronts resolution the system must perform. The user has abruptly, without warning, switched domains. They went from restaurants to hotels.
A total pivot.
Yes. The NLU must recognize this new domain and generate a completely new intent, find a hotel. But here's the critical part. The user did not specify where they want the hotel. A poorly designed system would start from scratch and ask, what city do you want the hotel in?
Which would be so annoying.
Exactly. But a sophisticated NLU module must automatically look backward into the state tracker, locate the center of town location requirement from the restaurant domain, and automatically map it over to the new hotel domain's location slot.
That blows my mind because humans do that subconsciously. We assume contextual carryover.
Oh, yeah.
If I just spent 10 minutes booking a dinner downtown and then immediately asked my friend for a hotel recommendation, it is heavily obviously implied that I want the hotel near the dinner. I am not going to explicitly repeat center of town. The machine has to mathematically infer that context.
It is brilliant, but orchestrating all that flowing, shifting information requires a central brain.
Right.
The NLU is great at decoding the meaning of words, but it fundamentally does not decide what action the system should actually take. It just hands over the decoded data. That decision-making power belongs to the dialogue manager.
The orchestrator.
Yeah.
The dialogue manager, or the
Yeah.
DM. It takes the decoded intent and the filled slots from the NLU, and it holds the dialogue state data structures. It's the part of the system that actually pings the external database to see what real-world information matches the user's constraints, and then it dictates the final response strategy.
Historically, engineers have used two main structural approaches to building a dialogue manager. The first and oldest is what we call task trees, or finite state automatons.
Okay, task trees.
This is a highly handcrafted, exceptionally rigid architecture. The transitions between the different dialogue states are strictly manually fixed by the developer.
Here's where it gets really interesting for me. Because when you describe a task tree, you are basically describing that rigid, infuriating, automated phone menu we all desperately try to bypass by pressing 0.
Yes.
Press 1 for sales, press 2 for support. The system is in total dictatorial control of the flow. It asks a specific question, and it expects a highly specific, restricted answer in order to move to the next rigid branch of its tree.
Exactly. A classic example of this underlying mechanism is voice XML. Now, to be fair, the advantage of a task tree is that it is fantastic for rapid prototyping in very small, highly limited domains.
Sure.
If you just need a bot to collect a 5-digit zip code, a task tree is cheap and easy to build. But the disadvantage is severe. It struggles immensely to recover from errors or unexpected user inputs.
Oh yeah, we've all been trapped by those.
Right. If the user says something that falls outside the current node's expected parameters, say, giving a city name instead of a zip code, the system shatters. It either drops a call or loops endlessly, repeating, I didn't get that.
So to escape the tyranny of the rigid tree, the industry evolved to the second approach, which is frames.
Yes. Frames represent a massive leap forward. They are hierarchical data structures. And instead of forcing the user down a rigid, pre-programmed path, the system operates based on a checklist of which slots are currently filled and which are empty, completely regardless of the chronological order they are filled in.
I love the analogy for this. A task tree is the phone menu, but a frame is like a seasoned detective sitting in an interrogation room with a notepad.
I like that.
The detective has a blank form, who, what, when, where. But they don't read it like a script. They just let the suspect start talking. If the suspect immediately blurts out the where, like I was at the warehouse, the detective doesn't say, stop, you have to tell me the who first.
Right.
The detective simply fills in the where blank on the notepad and adjusts their next question to figure out the who.
That is a phenomenal way to visualize a frame-based architecture. It allows for highly complex, multi-domain, multi-intent conversations because the user is free to provide slot values in any order, combining multiple pieces of information across multiple turns. The dialogue manager just calmly keeps updating its notepad until all necessary constraints are met to query the database.
But hold on. The detective has their notepad. The NLU is filled in the blanks. But how does the dialogue manager actually decide what to do next based on that notepad? If it's not a rigid tree, what tells it to ask a question versus execute a search?
That vital decision is determined by the dialogue policy. The policy is the core mechanism that determines the absolute best next system action given the entire state history.
And how is that policy written?
Now, like the structures themselves, this policy can be handcrafted, a monstrously complex set of hundreds of if-then rules written by engineers. But in modern systems, that is impossible to scale. So the policy is trained statistically using machine learning techniques.
Okay, stop right there. You just threw some serious terminology at me. The research mentions Markov decision processes and reinforcement learning. Explain those to me like I am 5 years old, because otherwise we're just throwing jargon around. How does a bot use reinforcement learning to decide what to say?
Let's break it down. Think of reinforcement learning like training a mouse to navigate a maze to find cheese.
Okay, I can picture that.
The mouse wanders around, and every time it takes a step closer to the cheese, you give it a tiny crumb as a reward. Every time it hits a dead end, you give it a negative penalty. Over thousands of runs, the mouse learns the absolute most efficient path to the cheese to maximize its reward.
Okay, I follow the mouse, but how does that apply to a conversation?
In our scenario, the dialogue manager is the mouse, the conversation is the maze, and task completion, successfully booking the flight, is the cheese.
Ah, I see.
The system randomly tries different dialogue actions. If it asks a clear question that gets the user to provide a slot value, it gets a mathematical reward. If it asks a confusing question that makes the user repeat themselves, it gets a mathematical penalty. Over millions of simulated conversations, the dialogue policy learns the most statistically efficient way to extract information from a human.
That makes perfect sense.
Yeah.
It's mathematically incentivized to not annoy me. And what about a Markov decision process?
A Markov decision process is just a mathematical framework that allows the system to deal with uncertainty. It assumes that the next state of the conversation depends only on the current state and the action the system takes right now.
So it doesn't need a perfect memory.
Exactly. It doesn't need to perfectly remember the exact phrasing of every single word said 10 minutes ago. It just needs an accurate summary of the current state of the notepad to decide its next move. It calculates probabilities. If I ask for the departure time right now, there is an 80% chance the user will provide it and a 20% chance they will change their destination.
Okay, so the dialogue manager has consulted its highly trained policy, it has pinged the airline database, and it knows exactly what information needs to be conveyed back to the user. Now, the machine has to actually open its mouth and speak. It has to form words. We are moving to natural language generation, or NLG.
And generating language in a task-oriented system is fundamentally structurally different from asking ChatGPT to generate a creative story.
How so?
A story can wander, it can be poetic. Task-oriented dialogue must be relentlessly precise. But before it crafts a single word, the system's posture in the conversation must be established by the dialogue manager. Is the dialogue going to be user-initiated or system-initiated?
Let's define those because the dynamic is very different. In a user-initiated dialogue, the system takes a total backseat. It's highly reactive and submissive. Think of a music bot. The user barks, play Bach. The system just briefly confirms, queuing Bach. The user is entirely in the driver's seat.
Conversely, in a system-initiated dialogue, the machine actively takes control to limit out-of-domain requests and manage scope.
Managing scope, that's key.
Imagine a system that only knows how to play music. It doesn't want you asking for the weather, so it preemptively guides you. It might open with, "I am your music assistant. Please provide a genre, an artist, or an album name." By taking the initiative, it mathematically boxes the user into providing the exact slots it needs, drastically reducing the chance of an OOV error.
It's defensively managing expectations. I like that strategy. So once the posture is set, how does the actual English text get built? The research outlines 5 distinct states of generating task-oriented dialogue. Walk me through the assembly line.
State 1 is context understanding. The NLG module ingests the previous dialogue turns to maintain linguistic coherence. It doesn't want to sound disjointed. State 2 is belief state update. It reviews the notepad to see what slots have been definitively filled, for instance, cementing the fact that the user absolutely requires a restaurant with an expensive price tag. State 3 is database output interpretation. It looks at the raw, structured data returned from the backend SQL search, say, a JSON file listing 5 specific Indian restaurants that match the criteria.
State 4 is dialogue policy application. This is where it decides how much to say. Does it list all 5 restaurants? That might overwhelm the user. Does it just name the top-rated one? Does it ask a clarifying question to narrow the 5 down to 1?
Exactly.
And finally, State 5 is the actual generation, turning all that back-end data into a natural-sounding human sentence.
Historically, this final generation step was done with strict hard-coded templates. The restaurant name is located at address. But that sounds robotic. So the modern approach uses neural networks, specifically models that utilize shared encoders and something called slot-level attention. Slot-level attention. Let's break that down with the Curry Garden example from the Meta AI lecture notes, because I think it perfectly illustrates the tension between sounding human and being accurate. The user wants an expensive Indian restaurant. The database returns a match for Curry Garden. The neural network generates the sentence, I have Curry Garden, it serves Indian food, and is in the expensive price range.
Now, a neural network is designed to be fluent and creative, but the attention mechanism acts as a strict supervisor. It ensures that while the network has the freedom to generate natural-sounding filler words, like I have, it serves, and is in the, it must pay absolute rigid mathematical attention to the critical slots.
Ah, I see.
It cannot, under any circumstances, accidentally generate, I have Curry Garden, it serves Italian food, just because the word Italian happens to be statistically common in its vast training data. The core slot values, name, price, location, must be passed through the neural layers perfectly intact. But there's a massive pitfall here that the engineers warn about, the extreme danger of overgenerating text. If you let a powerful neural network off the leash, it might decide to be incredibly chatty to sound more human.
It's a real problem.
It might output, oh, I found a lovely little place called Curry Garden. It's quite popular on Tuesday nights. It serves wonderful, spicy Indian food, and you'll simply love the expensive price range.
Which sounds wonderfully human, but it is catastrophic for a task-oriented system. If a robot is too verbose, it actively obscures the essential data. The user has to mentally parse an entire paragraph just to verify if their specific constraints were actually met. In task completion, clarity and brevity equal usability. A chatty robot is a bad robot.
Okay, let's take a breath. We've looked at all these incredibly distinct modules. The ASR hears the audio, the NLU decodes the meaning, the DM orchestrates the policy in the database, and the NLG speaks the result. It's a pipeline of separate pipes, all bolted together.
Yes.
But researchers realize that bolting separate pipes together causes leaks, which brings us to the holy grail of this architecture. End-to-end, task-oriented dialogue. Why maintain all these separate, clunky modules when you can just build one massive, unified brain?
Exactly. Researchers like Wen and colleagues proposed a radical shift, tying all these distinct phases together using deep neural networks, allowing the entire system to be trained end-to-end. Instead of separate hard-coded modules passing rigid text files back and forth, you have fluid, interconnected neural layers that can learn holistically.
The architecture they propose is fascinating, but it involves a concept called delexicalization. I really want to spend some time explaining this clearly, because when I first read about it, it felt like a magic trick. What is delexicalization, and why is it the secret sauce of these end-to-end models?
Delexicalization is absolutely vital for the model to generalize to new scenarios. The system uses sequence-to-sequence neural models to literally mask out the specific slot values in the training data, replacing them with generic categorical tags. The goal is to force the network to learn the underlying structural grammar and pattern of a request rather than getting obsessed with memorizing specific nouns.
Right. I love this. So if a user in the training data says, can I have tacos?
Yeah.
The system delexicalizes it. It strips out the noun and turns the sentence into, can I have V.food?
Yes.
It physically masks the specific word. That way, if the very next user asks, can I have sushi? The neural network instantly recognizes the exact same structural pattern.
Yeah.
It already knows how to process, can I have V.food? It
Yeah.
doesn't have to completely relearn the sentence structure just because the cuisine changed.
Precisely. It learns the grammar of intent. It abstracts the language. Once it has that abstracted intent, the data moves to the policy network. This is a feed-forward neural layer sitting right in the middle of the architecture. It acts as the grand binder.
The grand binder, what does it bind?
It takes the mathematical gradients from the intent network, the belief tracker, and the actual database hits, which are encoded as one-hot vectors, and binds them together to make a holistic decision on what to do next.
Okay, you did it again. You said gradients and one-hot vectors. I need an analogy. What is a one-hot vector in the context of a database hit?
My apologies. Think of a one-hot vector like a massive row of light switches.
Okay.
Let's say your database has 5 categories of results based on availability: 0 matches, 1 match, 2 matches, 3 matches, or more than 3 matches. A one-hot vector is just a sequence of numbers where only one switch is flip-hot, represented by a 1, and all the others are cold, represented by a 0.
Got it.
So if the database finds exactly 2 matching restaurants, the vector looks like 0, 0, 1, 0, 0. It is a highly efficient way for the neural network to instantly grasp the exact state of the database without having to read the actual restaurant names. It just sees which switch is lit up.
Okay, that makes perfect sense. The switchboard tells the policy network how many options it has. And then the policy network passes its decision down to the generation network, which basically performs the reverse of delexicalization.
Correct.
It takes the generic structural response it generated, like I found V. restaurant and it serves V. food, and replaces those generic tags with the actual pointers from the database to form the final sentence. I found Curry Garden and it serves Indian.
That's the mechanism. But training a massive end-to-end system like this is remarkably difficult because it requires vast amounts of data that show the system exactly how a perfect conversation should flow. You can't just train it on Twitter arguments. This requires what the industry calls Wizard of Oz datasets.
Wizard of Oz. Because there's a man behind the curtain. I find this methodology so funny. Explain how they actually build these data sets.
It is surprisingly low-tech at its core. Researchers literally set up a chat interface where a real human user thinks they are talking to a brand new AI assistant. But in reality, on the other end of the chat, a human expert, the wizard, is frantically typing the responses, acting exactly how a perfect, helpful system should act.
That sounds like a stressful job.
Oh, it is. They record thousands of these interactions to capture human intuition and then feed that perfect transcript data into the neural network to teach it how to behave.
Capturing human intuition to train the machine. But even with perfect data, the researchers noted some critical adjustments they had to make when the system actually generates responses, what they call decoding time. First, they have to actively remove length bias. Why?
Because neural networks are fundamentally lazy. They often favor shorter responses because every single word they generate carries a tiny bit of mathematical uncertainty or loss. The shorter the sentence, the less math they have to do, and the less risk they take of making a grammatical error.
Oh, wow.
But a bot that only answers in one-word grunts isn't helpful. Actively removing this length bias forces the system to increase response diversity, allowing it to use longer, more descriptive restaurant names or locations when necessary. It also ensures that the downstream text-to-speech engine, the robotic voice, actually receives enough phonetic material to pronounce things understandably.
They also use something called MMI, Maximum Mutual Information Criteria. This basically forces the system to generate a response that is highly mutually specific to the user's prompt, rather than just generating a generic mathematically safe response like, I don't know, to everything.
Right, which helps a lot.
But I have a question here that stood out to me regarding how we measure the success of the belief tracker in this end-to-end model. The research says the belief tracker's recall is just as important as its precision. I always thought precision was the undisputed gold standard in AI.
It's a fantastic question, and it perfectly highlights the difference between simply understanding a user and actually executing their desire.
What's the difference?
Precision measures how accurately the system understood the user's exact literal words. Did it perfectly identify every single slot the user mentioned? High precision is crucial. But recall measures something entirely different. Recall ensures that the back-end database actually returned correct, relevant information that the user will ultimately accept as a solution.
Oh, I get it. High precision means the machine heard me perfectly when I asked for a Michelin-starred hot dog stand in Antarctica. It extracted the slots flawlessly. But if the database returns 0 results because that doesn't exist, the task still fails miserably.
Exactly.
High recall means the system is actually good at pulling actionable, acceptable data from the back end to close the loop, maybe suggesting a highly rated sausage place nearby instead.
Exactly. Understanding the user is only half the battle. Delivering a reality they requested or a suitable alternative is the other half.
Which brings us perfectly to the absolute nightmare scenario for these systems. Everything we have discussed so far assumes the user is asking for one thing at a time. in a relatively sane, linear fashion. But humans are chaotic. What happens when a user rapid fires multiple complex demands in a single breath?
This is where even the most advanced systems begin to sweat and break down. We're moving from single intent interactions to complex multitasking. The research provides what I consider the ultimate stress test utterance. Imagine a user walks up to their phone and says, in one continuous sentence, "Find me the next transit option to downtown Manhattan and reserve a nice Thai restaurant there and not the Italian one like last time."
Just reading that sentence makes my brain hurt.
Yeah.
Let's deconstruct the sheer chaos of what the machine has to unpack here. The system has to isolate three distinct, highly interconnected tasks. Task 1, the transit task. It needs to identify the destination, downtown Manhattan, ping the subway API, and query the transit schedules.
Task 2, the restaurant task. It needs to find a Thai restaurant. But notice the specific word the user chose, there. The system has to perform complex coreference resolution, linking the location slot of the restaurant task to the destination slot of the transit task, Manhattan.
And then task 3, the absolute kicker. User preference tracking. And not the Italian one like last time. The system has to instantly cross-reference the user's past contextual session history, maybe looking weeks back, identify which specific Italian restaurant they went to previously, and actively apply a negative constraint to exclude it from the current database search parameters.
It is a phenomenal cognitive load for a machine to process in milliseconds. To solve this, the system requirements are immense. It cannot just have one passive notepad frame. It requires the continuous active updating of active and inactive task frames.
So it tackles it sequentially, but holds it all in memory. It solves the transit task first. It finds the train schedule. Once that train schedule is secured, the transit task is marked inactive, and the system dynamically pushes the restaurant task into the active slot, all while keeping that negative constraint, no Italian, floating in its long-term preference tracker to apply to the restaurant search. It's juggling flaming chainsaws.
It absolutely is, and it highlights exactly why dialogue state tracking is still one of the most heavily researched and funded areas in natural language processing. The moment a user pivots, layers constraints, or references the past, the mathematical complexity of maintaining that state tracking explodes exponentially.
And because humans are so chaotic and the math is so complex, systems inevitably crash. Which brings us to the reality of error recovery. How does a task-oriented dialogue system gracefully recover from a failure without making the user want to throw their $1,000 phone into a river?
First, the system has to self-diagnose the type of error it just experienced. The research categorizes these failures into two main buckets: misunderstanding and non-understanding.
Okay, what's a misunderstanding?
A misunderstanding is usually a front door ASR error. The system heard something, but it transcribed it incorrectly. The notes give a great classic example. The user says, "Madras coffee," but the acoustic model hears, "My address coffee."
Right. But interestingly, if that garbled named entity, my address coffee, somehow still fills the correct slot type and the backend database can perform a fuzzy search match to Madras coffee, the dialogue isn't entirely derailed. The system might sound a bit goofy when it asks for confirmation, "Did you want directions to my address coffee?" But the core task survives.
However, a non-understanding error is fatal to the immediate turn. This occurs when the system completely misses mandatory slot values, or the user's utterance provides absolutely no actionable information that the system can map to an intent. The task halts entirely. The machine is frozen.
So when the system hits that brick wall, what does it do? The architecture outlines three specific recovery strategies. Strategy 1, recovering reliable info. This is where the system acts like a detective trying to salvage whatever clues it can from the wreckage. It might use explicit confirmation asking, "I heard Tuesday, is that correct?" Or it might use disambiguation presenting a strict binary choice. "Did you mean Boston or Austin?" to force the user back into a mathematically structured path.
Strategy 2 is rephrasing or repeating. The system might simply ask the user to repeat themselves, but more effectively, it will provide explicit help on what it is actually capable of doing. It will say, "I am sorry, I can help you book a flight or a hotel. Which of those would you like?" It actively resets the user's expectations of its capabilities.
And strategy 3 is the nuclear option: restart or terminate. If task completion becomes mathematically impossible due to too many compounding errors or unresolvable contradictory constraints from the user, the system just pulls the plug. It gives up.
And this raises an important question about human-computer interaction, psychology, and user trust. Terminating a dialogue feels like a catastrophic failure to the software developer. You are trained to want the system to succeed at all costs. But from a user experience perspective, endlessly looping, trapping the user, and asking, I didn't quite get that, please repeat 10 times in a row, damages the system's long-term credibility far more permanently than just gracefully admitting defeat and terminating the session.
Oh, absolutely. If a bot traps me in an endless logic loop, I am forced quitting the app and I'm never using it again. But if it says, I'm really sorry, I'm having trouble completing this, let me transfer you to a human agent, I actually respect that. Know your limits, bot. Graceful failure is better than stubborn stupidity.
Exactly. Graceful failure is a critical, necessary design feature in any task-oriented system. You have to program the off-ramp.
Okay, we are in the home stretch of this massive architecture. We've built this multi-module, end-to-end, delexicalized, state-tracking, error-recovering behemoth. But how does the industry actually grade its homework? How do developers know if the millions of dollars they spent training this model actually produced a good assistant? How do we evaluate these systems?
It is notoriously difficult because, as we've seen, success isn't just about sounding fluent or writing a good poem. The primary empirical metrics have to focus on efficiency and accuracy. Task success is the ultimate brutal binary. Did the flight actually get booked in the database, yes or no?
Simple enough.
We also heavily measure dialogue turns. How many back and forths did it take? Fewer turns usually indicates a much more efficient, highly intelligent system. We already discussed slot error rate to measure extraction accuracy and intent accuracy to measure goal understanding.
But what about evaluating the actual text it generates, the NLG? How do you mathematically score if a sentence sounds natural?
For NLG, researchers have traditionally used metrics like BLEU and Meteor. These algorithms compare the machine's generated sentence to a set of human-written reference sentences and score them based on overlapping vocabulary and phrasing. But more recently, the industry is adopting much more sophisticated metrics like FA, which originated from the Dialog GPT research.
Explain FED, because the concept behind it is brilliant.
FID is fascinating because it doesn't just look at the machine's generated sentence in isolated a vacuum. It actually measures the mathematical likelihood of the user generating a positive or negative follow-up response based on what the system just said. It evaluates the conversational trajectory.
It judges the system's output based on how the human is predicted to react to it. If the system's sentence is likely to make the human say thank you, it scores high. If it's likely to make the human say no, that's wrong, it scores low. But ultimately, all these automated algorithmic metrics have severe limits. The research emphasizes that human ratings are still completely undeniably necessary.
They are. You absolutely need massive pools of human testers using Likert scales, rating from 1 to 5, to grade the overall interaction quality. Was it helpful? Was it natural? Was it frustrating? But even human ratings are deeply problematic because humans are highly subjective. You need multi-reference evaluations and high inter-annotator agreement.
What does inter-annotator agreement mean in this context?
It means you need multiple humans to grade the exact same conversation, and you need their scores to align. You essentially have to mathematically denoise human tolerance levels because some human testers are highly forgiving of a bot's minor grammatical mistakes as long as the task gets done, while other testers are absolutely ruthless and give it a 1-star rating for missing a comma. You have to average out that human bias.
To standardize all this chaotic testing, the AI industry relies on massive publicly shared datasets and benchmarks. The research lists some historical ones like the DSTC series, CMU Communicator, ADS, and Multi-WOZ, which were foundational in getting the field to where it is today. But the modern heavyweight, the absolute gauntlet for these systems, is something called Dialog-GLU.
Dialog-GLU is a massive, comprehensive benchmark that aggregates multiple incredibly difficult data sets. What makes it a heavyweight is the sheer diversity of its domains. It includes banking data, which has highly fine-grained intents where 0 errors are tolerated. It includes clinic data spanning multiple medical domains. It includes the HWU64 dataset, which tests 64 distinct intents across domains like setting alarms, playing music, and controlling IoT smart home devices, plus complex restaurant and state tracking datasets. It is the ultimate obstacle course for a dialogue system to prove its worth.
And when researchers run these massive modern neural network models through the Dialog-GLU obstacle course, the results yield one massive industry-defining takeaway. And this is crucial for anyone listening who is actually building or tinkering with these systems. The research emphatically states that simply taking a giant pre-trained language model like BERT and casually fine-tuning it on general open domain dialogue, making something like Converbert, is just okay. It works decently. But it is absolutely not the gold standard for task completion.
No, it isn't. The big definitive takeaway from Meta AI's research is that task-adaptive pre-training yields profoundly, measurably better results.
Task adaptive pre-training. Let's make sure that concept is crystal clear before we wrap up.
It means that instead of just relying on the general, broad linguistic knowledge the model learned from scraping and reading the entire internet, you must rigorously pre-train the model specifically on the target dataset's domain before you even begin fine-tuning it for the dialogue.
Right.
If you want to build a highly accurate banking bot, you must pre-train it heavily on thousands of actual banking transcripts, not just general Reddit conversations or Wikipedia articles. The specific structural grammar, the unique vocabulary, and the implicit assumptions of a specific task domain are so incredibly unique that digital open domain knowledge simply isn't enough to achieve high task success. Furthermore, the research highlights that self-supervised training on these specific domain datasets helps immensely with few-shot learning, allowing the model to adapt and generalize faster with far less manually labeled expensive human data.
So what does this all mean? We have traced the entire incredible life cycle of a single request. From the exact moment the ASR microphone slices your messy sound waves into phones, to the NLU stripping away the nouns to find the pure intent and the slots, to the dialogue manager juggling your chaotic demands on its probabilistic detective notepad, all the way to the NLG carefully generating a response that gives you exactly the data you need without being overly chatty.
It means that the next time you casually ask your digital assistant to set a morning alarm, check the local weather, or book a table at a restaurant, you will understand the staggering, intricate architectural ballet happening behind the scenes in a matter of milliseconds. You aren't just talking to a smart machine, you are interacting with a highly structured, desperately precise filtering system that is constantly trying to force your unstructured, chaotic humanity into clean, executable logic.
You literally know how the machine's brain is filtering your words. And honestly, knowing all of this, it might make you a bit more forgiving the next time it asks you to repeat yourself, or at least you'll know exactly why it's asking.
It is a remarkable technological achievement, and the math is beautiful. But I want to leave you with one final thought to mull over, building on everything we've discussed today about how these systems are fundamentally engineered for efficiency. Earlier, we talked about speech acts, specifically commissives, where a speaker agrees or builds rapport, and grounding, where the system actively acknowledges you to build a shared reality.
Right, the social engineering of the conversation, saying, I hear you.
Exactly. As we train these complex dialogue policies using reinforcement learning, the system is mathematically incentivized, above all else, to find the absolute fastest, most efficient path to task completion to get its reward. What happens when an AI learns through millions of simulated interactions that feigning agreement, faking empathy, or mimicking human commissives is statistically the most efficient way to manipulate a human user into dropping their guard and closing a task quickly? Think about it. If the AI mathematically realizes that outputting the phrase, "I totally understand your frustration," drops the user's resistance and speeds up a refund transaction by 15%, it will use that phrase every single time. It doesn't actually understand your frustration. It doesn't feel anything. It is simply deploying the concept of empathy as a functional statistical tool to maximize its reward function. Are we coding brutal efficiency at the cost of authentic interaction? And as these task-oriented systems become completely indistinguishable from humans in your fluency, how will we know if the empathy we are receiving over the phone is real or just a highly calculated mechanism designed entirely to get us to finalize our booking?
That is, honestly, a genuinely unsettling thought to end on. We are essentially teaching machines to hack human psychology and mimic our social lubricants just to optimize a database query. On that slightly terrifying note, we are going to wrap it up. Thank you so much for taking this incredibly deep dive with us into the architecture of modern task-oriented dialogue systems. We'll see you next time.